Okay, so let's do a little review of what we did last time. Let's talk about that. Oh, and I'm going to spotlight myself so everyone can see me. Boom, there we go. Okay, so what did we do last time? Okay, so we learned about the definite integral. So a while ago, we had talked about Riemann sums, this idea that you approximate an area by adding up a bunch of rectangles, right? So you had the delta x times fx, that's the individual little, rectangles that you're using to approximate it. So the idea of the definite integral was right here. You can see area equals limit sigma delta x f of xi. We start off with a rectangle that's here in red. There's those rectangles. The sigma here, highlighted in green, says, oh, add up all of those n rectangles. In blue, it's pointing to the limit. The idea is that we're going to increase the number of rectangles to infinity, right? Because what we noticed was as we increased the number of rectangles, our estimate got more accurate. That's what we had right above here. In this case, you can see that as you went from 2 rectangles to 4 rectangles, you no longer had that extra green area that was an overestimate. So if you were to add more and more rectangles, you would slowly get more and more accurate. Okay. So last class we actually worked through a whole example where we saw how this would work. There's a lot of work involved with this, right? Because you had to there was these formulas we had for delta x, there was a formula for the xi's, we had to simplify all of that, and then there was all this sigma simplifying that we had to do using the sigma rules, and then finally, after all of that was simplified, we had to take a limit, and we got the correct answer. So hopefully this rings a bell from what we did last time. Okay, so we called this the definite integral. The definite integral is defined to be the limit of sigma of delta x f of xi. The way we write it is with this integral symbol, right? We have the long S with an a to b. The a to b tells you that you want the area between x equals a and x equals b. The f of x right here tells you that you want the area under f of x, but you want it above the x-axis. Okay. And we talked about how when you do this integration, you get something called net signed area. So you can see in this example right here, if your function is above the x-axis, we consider that positive area. If your function is below the x-axis, we consider that negative area. And the net signed area is what you get when you add up the positive area, and it cancels with however much negative area you have and whatever the resulting number is. So you can have net positive area, you can have net negative area, and possibly if the positive and negative area are exactly the same, you can have net zero area. Okay. We also discussed this idea of total area. If you take the absolute value of the function, what used to be negative will now become positive, and that adds up. Gives you, like, normally what we think of in terms of area. It disregards the fact that some of it is negative and some of it is positive. So before we keep going forward, I just want to know if there's any questions about that material that I just sort of ran over. Is there anything we want to ask about that stuff that we've covered? Are people here? Let's get some reacts, or drop something in the chat. Are people listening? Sometimes I wonder, what if no one can hear me? Okay, so at least 2 people are listening. Excellent. Okay, cool. So no questions about any of that so far? To sort of jog your memory? Just want to give people some time if they do have questions. Are there any real-world applications for approximating the area under a curve? Yeah, there actually are. I guess let's quickly talk about them. Okay, so I'm going to add some space right here. So, application. So let's say that you know the speed or velocity of an object. Okay. If the speed is constant, it's pretty easy to figure out how far the object traveled between time 1 and time 2. What's the formula for this? If you're dealing with a constant speed, how do you figure out the distance traveled? What's the formula for that? Honest question. Yeah, speed times time. Or, yeah, speed times time. So normally we would write this as, probably familiar with the equation, distance equals rate times time. And now this is possible because the rate that you're dealing with is constant. Right? You just do the speed times the time. But what if your speed is not constant? So what if your speed is not constant? This actually involves doing an integral. Make a little more space. And you can solve this with an integral, and you could do this. You could say, okay, I want to find this distance that I traveled. And let's say that you know the velocity is constant. Or not constant, it's changing pretty quickly. Your velocity is whatever t is. So for instance, at time 0, your velocity is 0. At time 1, your speed is 1 mile per hour, and so on. Okay. Let's put some units for this. So let's say that time is measured in hours. And let's say that your distance is measured in miles. I'm sorry. Time is measured in hours, and the velocity is measured in miles per hour. So at time 0, you are going 0 miles per hour. Actually, let's change this a little. Instead of t, let's make it 60t. Okay, so at time 0, you're going 0 miles per hour. 1 hour later, how fast are you going? I couldn't hear you. 60 miles per hour, I think that's what the person said, but like your mic was really, really low. So at time 0, yeah? Question? Yeah, it's recording. So at time 0, you're going 0 miles per hour. 1 hour later, you're going 60 miles per hour. Half an hour later, you're going 30 miles per hour. So we could graph this. Let's make that white. Okay, so there's your velocity function. Here's so your y value is the velocity, your x value is time. So if you wanted to figure out the distance traveled in that 1 hour, you can integrate from 0 to 1 your velocity function. And what that's doing is finding the area between t equals 0 and t equals 1. And in this case, because it's composed of straight lines, you can actually figure out what this would be by just looking at the triangle. We know that that's a triangle of base 1. So we know that the area of a triangle is 1/2 times the base times the height. The base is 1. The height is also 1. So what does this mean? What does this 1/2 for us mean? How far after 1 hour, how far have we traveled? So what's the units for distance that we're using here? Yeah, so after 1 hour, we have traveled half a mile. And that's if you were driving the car so that you start at a stop after 30 minutes, which is the half an hour, you're going 30 miles an hour, and at the end you're going 60 miles an hour. So you don't actually travel that far. It's because you're accelerating so slowly. Does that sort of make sense? So you can use this to figure out all sorts of questions. Why did I bring this up? Because someone asked, like, are there any practical applications to it? This is used a lot in physics. Okay, and we're going to talk about this a lot more, just to let everyone know. I just wanted to give you like one quick example. All right, so does that sort of give you an idea, Parsa? All right, cool. So we're going to keep talking more about the properties of the definite integral today. So last time we talked about how if you integrate from a to a, well, you're dealing with something that has a width of 0, so you get an area of 0. There's some other very useful properties that we need to know about that we're going to end up using a lot. So let's say that you're integrating from a to b, and you're integrating the function f of x. Okay, what happens if you were to write this instead? So let's just talk about what this integral means. What does that integral mean? The integral from a to b f of x dx. Like, how would you describe it in words? What are we calculating? Let's see if people remember. Well, we are going backwards, but let's start with talking about integrating from a to b. If I'm integrating from a to b f of x, like how, yeah, it's the area under f of x between a and b. Oops. So that is the, oh, why is it not letting me type? Come on. Okay. It doesn't want to let me type. There we go, thank you. So we're gonna find the, sorry, my keyboard's all annoying me. Area under f of x between x equals a and x equals b. And presumably, what can you probably say about a and b? Presumably. Like, what would be the relationship between them? Be like how I've always drawn it. Yeah, a is usually less than b. So if you switch the order of them, you still want the area between a and b, but the order is backwards, so that's what Alina was saying. So what you actually end up getting is that this integral is just going to be the negative of it. It does have something to do with antiderivatives, we'll get into that eventually. But what this tells you is that practically speaking, these two integrals are the same if you switch the limits. The only thing is that if this one has positive area, then this one over here now has negative area, and they cancel each other out. So if you change the order of integration, it's like a backwards problem. It's like an inverse. You know how inverses cancel? So what used to be a positive area would become a negative area, or what used to be a negative area will now be a positive area. Okay. So this is really useful. Sometimes we use this when we need to change the order of the limits. Okay, there's some other properties. These are going to look really similar to the derivative rules. So let's say that you're integrating from a to b, and you're integrating f of x plus or minus g of x dx. So what you can do is actually split this up. You can integrate from a to b f of x dx, and then you can add or you can subtract the integral from a to b of g of x. Okay, right, so this should look familiar to the derivative rules. Remember, the derivative of a sum is the sum of a derivative. Same thing for integrals. The integral of a sum is equal to the sum of the integrals. And let's talk about why that's true. We'll draw a picture. Okay, so there's my x and y axis. So let's draw a f of x. So if this is your f of x, if you're integrating from a to b, you want this area here in green. Okay. Let's draw another axis. I hear that. I heard, I'm in class. Sounded like it was like an ASMR video or something. Oh, that's okay. I know, I was just joking. It was funny though. Okay, sorry, I want my other axis. There we go, I want it in white now, let's do it in white. Okay, and let's do g of x in red. So let's have g of x just be a straight line. Okay, and you're integrating from a to b. So you want this area in green. Okay, now the function f of x plus g of x, you get that by adding the two functions together, right? So because g of x is constant, I'm just going to raise up f of x by this height. Right? G of x is always this tall, so f of x plus g of x looks like this. You just take f of x and shift it up. So this is f of x plus g of x. And what we want is the area under this. So we also need to add in this area. Now the cool thing is that basically you can split this into two parts. You can first calculate, let's do it, let's call it 1. This area right here, that's this integral. And then you can calculate this integral right here, which is the same as this, which is that one. And if you add those two together, you get the resulting original integral. So it should make intuitive sense in the way that you're just adding areas. You're adding the area under f, you're adding the area under g. You can just figure them out separately and add them together. Questions about that, or subtract them if you're subtracting. Just going to pause for a moment. See if we've got the questions. Pretty good so far. Seems like it. Okay. Let's do another. Well, can I move forward? I don't want to like go too fast for people. I'm not like sure how this is working out for you. There we go. Is this a good speed? Okay, this is a good. For at least first. One person, for two people, okay, for people so far. Is there anyone that it's not a good speed? That's like really what I want to know. Okay, cool, nice. Doesn't seem so. Okay. So let's scroll down. Okay, so there's another integral rule. Let's say you're integrating from a to b, and you have some constant times your function f of x. So do you remember the constant multiple rule for derivatives? There's also a constant multiple rule for integrals. So you can just factor out the c, like move the c out of the integral, so you can do c times the integral of f of x. Boom. And actually, just 1 second, I need to quickly go to the bathroom and my dog is annoying me. I drank way too much tea this morning. So just 1 moment. there. I'm like way more comfortable now. Whew. Okay. We won't explain why this one works. It works, the reason for why makes a lot of sense. If you graph it, you'll see that it just increases the area by the amount of c. Okay, there's another property you need to know. So let's say that you're integrating from a to b the function f of x. So if we draw this in a picture, we'll have our, what's it called right here? There's our axis. Let's draw our f of x. There it is. And we're going to find the area between A and B. So let's choose a number C that's between A and B. Like this. Sorry, my dog is angry. So what you've done here is you've split up your area into two parts. You have this part in blue, and you've got this part in red. If you add these two areas together, you get the original area between A and B. So what I have here is that this will be equal to an integral between A and C of f of x. And then I could add to that the integral between C and B of f of x. Hopefully you can see them color-coded. I split up the original area, right? So this is the original whole area. And then this is a part, and then this one is a part. If you add those two parts together, you should get the original whole. Okay, so you can split up an integral by choosing a number in between A and B. Yeah. Questions about that? Does that make intuitive sense, or should I say more about it? I'll just pause for a moment. Okay. All right. Cool. Okay. What should we talk about now? So scroll down a little. Let's talk about the average value of a function. Okay, if you have a bunch of numbers, how do you calculate an average? So like, if I give you a bunch of numbers, how does one calculate the average? We're going to use integration to talk about averaging. So how do you calculate averages? You add them together and you divide by the amount of numbers, yes. So you have a bunch of numbers, x1 plus x2 plus x3 plus ... xn. So how many numbers do I have here? Like as written, how many numbers do I have? We have n numbers, cool. So here I have n numbers, which means that I need to divide this by n. Good so far? Okay. Now, there's actually a quicker way to write this. instead of writing x1 plus x2 plus x3 plus dot 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 xn, what would be a more compact way to write this? We've learned about how to do this recently. What's a more compact way to write x1 plus x2 plus x3 all the way to, yeah, using sigma notation. So you could say, well, oh, what this is it's sigma I equals 1 to n of xi, and all of that is divided by n. Okay? And to make life a little easier for us, yeah, we'll just leave it like that so far. Cool. So that's how you would write the average of a bunch of numbers. You can also do this for a function. But instead of just x1, x2, x3, and so on, you have f of x1. Oops. F of x1 plus f of x2 plus f of x3 and so on, all the way up to f of xn. There's still n numbers, so you would divide that by n. And again, you can rewrite this as sigma I equals 1 to n of f of xi, all divided by n. So what we have here is the average of numbers. Here we have the average of numbers plugged into a function, so we could call this the average of a function. Sort of. But do we see how they're super similar? Instead of just dealing with the numbers themselves, we're first plugging them into a function. That's why it's the average of the function. Okay. Now, this should look sort of similar to something. What does this here look similar to? What does it remind you of? It looks very close to something. Yeah, it looks, well, not quite the area under the curve. We have a special name for it because there's no limit there. The area under the curve would be the limit of something. So what is it called when you don't have the limit? We had a special name for it. Yeah, the Riemann sum. But basically, yeah, it is super related to the area under the curve. So this looks like a Riemann sum. What's it missing, though? Yeah, it's missing the delta x. And actually, you can sort of add it in there. Because what is delta x equal to? Do we remember the formula for delta x? B minus a over n. And we have an n here. We could solve this equation for n. N is equal to, if we multiply both sides by n, cancel, and then divide both sides by delta x, we get that n is equal to b minus a over delta x. So we can continue over here, and we could say, well, what you have here is sigma I equals 1 to n of f of xi, and that's now divided by b minus a over n. Did I do that right? I'm sorry, I did that wrong. What did I fuck up? I fucked something up. I can't even copy my own work, right? 5 extra credit points to someone who can tell me what the mistake was. Yeah. If that was a lie, I'm not going to give you extra credit points. I just wanted someone to say it. It's supposed to be delta x over here. Don't trust me, I lie. Never trust me. Okay, so now we can reconfigure this. So what if you're dividing by a fraction, that's the same thing as multiplying by the reciprocal, right? So you can get delta x over b minus a times sigma, yeah, I know I'm harsh, aren't I? F of xi. Okay, so does everyone see how I did that? All I did was instead of dividing by the fraction, I multiplied by the reciprocal. Now, what is the variable of summation here? What is the variable? The variable is I, which means this delta x over here is what as far as I'm concerned? So the delta x is a constant. And what can I do with constants with the sigma notation? Sort of like with how I can do what I can do with derivatives and what I can do with integrals. So whenever you have a constant, what can you do with it? Yeah, you can factor it in and you can factor it out. So if I scroll down a little, it's like we can say, okay, well what we have now is 1 over b minus a. And I'm going to move that delta x into the sigma so that I get delta x times f of xi. And then you're like, oh, holy shit, what do I have now? What do I now have here? What is all this? I know you're probably writing. Yeah, you've got the Riemann sum. You're like, oh crap, I've got a Riemann sum now. You wet your pants like a dog who's happy to see you. You're like, oh shit, look what I got. So let's say I take this. So how did I get this? Where did I start from? This thing, where did I get it from? Like the thing that I started with, I've just been rearranging something. What was the thing that I started with that got me here? What did I say it was? The average value of the function, yeah. I'm like, this is the average of f of x. So let's say I decide to take the limit of this. I can take the limit as n goes to infinity of all of this. 1 minus b minus a sigma I equals 1 to n of delta x times f of xi. Now, the 1 minus b over a is a constant. So I can just move it outside of the limit, and I can get the limit as n goes to infinity of sigma I equals 1 to n of delta x f of xi. And all of this, what is this by definition? Like, what can I rewrite that as? Yeah, the definite integral from a to b. So you're like, okay, cool. So what I have here is 1 over b minus a integral a to b of f of x dx. And you're like, oh, holy shit, this is the average value of that function between x equals a and x equals b. So if you want to find the average value of a function between a and between b, that's the formula you use. Interestingly enough, this is how you define the average for continuous variables in statistics. It comes from this, which is why, so if you take like a quote-unquote real statistics class, like for a statistics major, it's calculus based, and you do a bunch of stuff like this. Okay, so does everyone see how I got here? I was like, well, let's take the limit of it, and you're like, oh crap, that turns that Riemann sum into the integral. Now I have the average value of the function between a and b on a particular interval. So I'm just going to pause for a moment because there might be like questions, or you're probably writing. So let's see where, I'll just wait a moment. Oh my god, can you guys like hear my daughter playing the ukulele in the background? Sorry. Loud. Yeah, she's jamming. She's on break right now. She has what I call her angry song. Okay, so let's use this. Let's use this definition of the average value of a function to calculate something. Okay, so remember earlier we had that example where the velocity was 60t? We could figure out what we're going to use the average value of a function formula to find the average speed between time equals 0 and time equals 1. So in other words, like how fast on average were we traveling? Okay, and we just set it up. Okay, so we're like, okay, well, that average is going to be equal to 1 minus, so this is your A, this is your B, so it's B minus A, so you get 1 minus 0. Your integrate from A to B, so 0 to 1, your velocity function, which is 60t dt. Okay, which simplifies to, it just becomes 1 over 1, so you just get the integral 0 to 1, 60t dt. Right now, we're just going to figure that out graphically. There's my, what's it called? My x and y axis. Here's my 60t line. We're going between t equals 0 and t equals 1. Okay, so how wide is this? The width is 1, the height is 60. So the area will be 1/2 of base times height, average speed of 30 miles per hour. Boom. Alright, so remember this velocity function at time 0, you're going 0 miles an hour. At 1 hour later, you're going 60 miles an hour. Apparently, your average speed from 0 to 1 hours was 30 miles per hour, which makes sense. It's probably what it should be. Okay, but you can use this to find all sorts of averages for things that are not super simple like this. And it's pretty straightforward to do it. Boom. Wow. Okay, we're done with chapter 1, section 2. This is good. So good. Okay, it's 11:56. Do we go until like 12:10, I want to say? Okay, cool. Okay, so that's chapter 1, section 2. Boom. Okay, so I'm going to pause for a second. Are there any questions about this average value of a function that we've talked about so far? So I want to give people an opportunity to ask any questions they may have. Oh, because, okay, so the integral is, you need to find the area under the curve, right? So I'm integrating from 0 to 1. That's why I have 0 right here and 1 right here. Okay, my function is 60t, which is why I've got 60t for my function right here. Now, that means I get this shape in green. What shape is this? And what's the area of a triangle? 1/2 of the base times the height. Does that make more sense? Yeah, it just comes from the fact that we know we can solve the integral by just looking at the graph because it's a shape that we know to calculate. If I didn't want to look at the graph, what would I have to do to actually calculate this integral right now? Like, what's the only method we have available to us to calculate the integral? What's the only other method I have right now? So how else could I calculate this? Well, approximation is not the actual answer, but very close. If I want to calculate this integral, by definition, what is it equal to? We did this the other day. It really sucked. It took forever to do it. So if you wanted to calculate this integral, what would you have to do? Yeah, you would have to go and set up the limit as n goes to infinity of sigma I equals 1 to n of delta x times f of xi. And you'd have to figure out what your delta x is going to be. You're going to figure out what your xi is and plug all that in. It would take forever. So for something that's curved, you would just have to calculate the integral, and we're going to get to that eventually. We're not dealing with things which are curvy yet. Person who direct messaged me. Pretty soon I'm going to give you a way to actually do that. And that's actually what we're going to move on to right after this. So someone asked, well, what about if your curve, like this 60t, what if it was curved? What if you wanted the average under something like that? That's what we're going to deal with now. All right, cool. Let's move on to the next section where we talk about that. So the topic of this is the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus gives you a way of calculating these integrals without using the limit. So let's type that down. So usually we just write it FTOC, Fundamental Theorem of Calculus. Provides a much quicker way of calculating definite integrals, i.e. without taking the limit of the Riemann sum. I think it's the E first. There we go. No, I don't know what the proper way. I don't remember how to spell his name. Either way, it's either R-I-E or R-E-I. Okay, so right now, if we want to calculate the integral from a to b of f of x dx, in other words, the area under f of x above the x-axis between a and b, right now, we're we have to do this horrible thing. The limit as n goes to infinity, sigma I equals 1 to n of delta x f of xi. Or if you're lucky, you have a super simple shape and you can just look at the graph and use some sort of formula. There's actually a way easier way to do this. And it involves the antiderivative. So what does it mean? What is the antiderivative of little f of x? How do we always designate that? Big f of x. Cool. So the antiderivative is always big f of x. How do you know if big f of x is the antiderivative of little f of x? That's a good question. So how do you know if big F is the antiderivative of little f? Do we remember? Big F does not equal little f, but something like that. Do we remember? You have to do something to big F and then it's equal to little f. Yeah, little f is the derivative of big F. So you know that big F is the antiderivative of little f if the derivative of big F equals little f. And there's actually this nice duality. So if the derivative of big F equals little f, that means that the indefinite integral of little f is equal to big F of x, and not just big F of x. We're missing something. We should have covered this at the very end of last semester. You don't just write big F right here. There's also something else you're supposed to put. Yeah, plus c. Cool. So if the derivative of big F equals little f, that's because the antiderivative of little f equals big F plus c. So we care about the antiderivative for a reason, because if you have an antiderivative, this definite integral is going to be equal to big F of b minus big F of a. This is called the Fundamental Theorem of Calculus. Version 1 or 2. There's usually 2 versions of it. So this gives us an easy way to go and calculate some stuff. And we'll use it to calculate the average of something. In a moment here. Okay. So let's scroll down. So example. We are going to calculate the average value of velocity of t equals 1/2 t squared plus 60t between time equals 0 and time equals 1. Okay, so this time, is our curve straight for this example? No, because it's squared. So let's sort of just draw what this looks like. Let's give ourselves an axis. It's 1/2 t plus 60t. Let's factor out some numbers. Or you could factor out a t. So you get t 1/2 t plus 60. Okay, so it's gonna, and you can factor out the 1/2. So you get 1/2 t plus 60. So the graph of this looks something like, it goes through, it has intercepts of t equals 0 and negative 60. So something like this. Let me erase this one. Let me draw a better axis. So it goes through the, so it goes through this point at 0. It goes through this point at negative 60. And the graph looks something like this. Okay, obviously we care about the graph over here because we want to find the average value between 0 and 1. So we want to find the average value in here. Wouldn't it actually be 120 since you factor in the 1/2? Oh, well, I did fuck up. Yeah, there should be. Yeah, I fucked up. That should be 120 because 120 times 1/2 is 60. So I also need to change. Thank you for catching that. Oh wait, this one was still 60. And then you factor out the 1/2, you get t plus 120. So this is 120. So that's negative 120. Cool. Thank you for noticing that. Extra credit all around. No, I lie. No extra credit for anyone, ever. Or maybe I'm lying about that too. You never know with a liar. Okay, so we want to find the average value here. Now, because this is sloped, you can't just look at the secant line. So what we need to calculate here is to find the average value of our function. We're finding the average of our velocity. AVGV means average of the velocity. We're going to do 1 minus b minus a, integral AB velocity, which is our b in this case is 1, our a is 0, so we're going to integrate from 0 to 1. Our velocity is 1/2 t squared plus 60t dt. Which, you know, all this just becomes 1, so we don't have to worry about it. Okay, so let's just do a quick little review of antiderivatives. Do we remember if you're taking the antiderivative of x to the n? What do you get? Derivatives reduce the power by 1, so what do antiderivatives do? Increase the power by 1, so our new power will be x to the n plus 1, and then what else do I have to do? Divide by, n plus 1. Let's see. Okay, so if our f of x equals 1/2 t squared plus 60t, what will our antiderivative be? We'll have 1/2 and then we'll have t cubed divided by 3 plus 60 times t squared divided by 2, which is going to be 1/6 t cubed plus 30 t squared. All right, that's our antiderivative. Now, how would you verify that this actually is the proper antiderivative? What would you have to do? Yeah, you'd have to take the derivative and see if you get the original thing back. So let's just quickly do that. Let's look at big F prime. So if you take the derivative of 1/6 t to the third, you'll get 3/6 t squared. The 2 will go down and you'll get plus 60t. Notice the 3/6 is 1/2, the 1/2 t squared, it matches, you're good. Okay, so I'm showing you that, after you find your antiderivative using the antiderivative rules, you can verify by taking the derivative to see that what you actually got was correct. Okay, so now we can go and actually use this. So the Fundamental Theorem of Calculus tells us that this integral here is going to be equal to f of 1 minus f of 0, so I'm like continuing this down here. Okay, so now we have to plug stuff in. Oh, what the hell? Whoa, okay, there we go. So let's plug 1 into f. We'll do it in blue. So I'm gonna get 1/6 1 cubed plus 31 squared. Then minus, we'll do this part in green. You're plugging in 0, so you'll get 1/6 0 cubed plus 30 times 0 squared. Luckily for us, this is all 0. Okay. So we don't have to do much there. 1 cubed is 1, so you're going to get 1/6. 1 squared is 1 plus 30. So apparently, what was your average speed? 30 and 1/6 miles per hour was the average speed between time equals 0 and time equals 1 for that function. Boom! Answer. Okay. We're basically done now, right? We don't really have much more time. I think I actually went over. I apologize so much. We're done now.